3.6 is implicit differentiation. This section uses all of the rules of differentiation that we have already been shown throughout the chapter. These consist of product rule, quotient rule, and the chain rule. The only difference is that we're now having two variables in our equation. Both of these variables are in terms of x. The first variable, called the argument, is represented by y. The constant, represented by x, will always derive to x prime. The argument, therefore, will derive to y prime, or dy over dx. The reason we use implicit differentiation is because it solves for complex graphs that cannot be defined as functions. For example, circles, the Folium de Descartes, or the Devil's curve can be easily solved with implicit differentiation. Here we can see the Folium de Descartes. Normally, three functions would need to represent the graph, as shown by the pink, the blue, and the yellow lines along the graph. By having two variables, x and y, we can represent the curve with just one equation, the red line. A simple example of how implicit differentiation can work better than explicit differentiation can be seen with the graph of a circle. To implicitly derive the function x squared plus y squared equals 50, we simply would use differentiation for x squared and y squared. This derives to 2x plus 2y y prime equals 0. Through subtraction, 2y y prime equals negative 2x. Then with division, we find that y prime equals negative x over y. When we plug the point of the tangent line into this solution, we find that the slope is negative 5 over 6. On the other hand, to explicitly find the slope, we would need to first take the square root of x squared plus 50. Then we would derive both sides using a more complex chain rule where y prime equals 1/2 50 minus x squared raised to the negative 1/2 times negative 2x. Then, after reducing the fraction, we have to realize that the square root of 50 minus x squared is actually y. Only then would we get that y prime equals negative x over y, and that the slope of the tangent line is negative 5 over 6. For this next example, we use implicit differentiation with product rule and trigonomic differentiation. Again, derive both sides of the equation. Remember that numbers just derive to 0. For the left side of the equation, use the product rule. Then take all of the expressions with y prime to one side of the equation, and again isolate y prime through factoring. After dividing both sides of the equation by 2x squared y plus x cosine y, we'll have the answer of y prime. This third example might look a little more complicated, but it really just uses all the same rules we've known before. First, derive using the rules we know for e raised to an exponent. In this case, it's raised to another expression, so you'll have to use the chain rule and the derivative of trig functions. Once again, e raised to the sine y derives to e sine y cosine y, and don't forget this part, times y prime. Then isolate y prime by first subtracting e raised to the cosine x times negative sine x, leaving on the left-hand side only the parts that use the variable y. Then divide by e raised to the sine y times cosine y to find y prime. In review, implicit differentiation solves for the slopes of graphs that are not functions since they don't pass the vertical line test. This means that we're using two variables that are in terms of x. For this reason, y derives to y prime, or dy over dx. Here's a short quiz for you to take that reviews the concepts we have learned in this section. For problem number 1, find y prime if sine x plus y equals y squared cosine x. For problem number 2, find y prime if x cubed plus y cubed equals 6xy. Here are the solutions to the short quiz. If you have any trouble looking through these steps, just look back in the video. Now that we all have a great handle on implicit differentiation, we can see some applications of it. Using implicit differentiation, we can see the proof of how to derive inverse trig functions. When y equals arcsine x, we know that sine y equals x. If you differentiate sine y equals x implicitly, you get cosine y prime equals 1, or y prime equals 1 divided by cosine y. From here, we see that cosine y equals the square root of 1 minus sine squared y, and that is the same as the square root of 1 minus x squared, because earlier, sine y equaled x. From here, y prime equals 1 divided by cosine y, or 1 divided by the square root of 1 minus x squared. 1 divided by the square root of 1 minus x squared is the derivative of arcsine x. Using the same proof of implicit differentiation, we have the following rules for all of the inverse trigonometric functions.